Okay, here is the first example. By using Routh-Hurwitz criteria, find the stability, whether this system is stable or not. So here is the characteristic polynomial equation. Okay, and, the order of the system is 6, so it has 6 poles. So we want to find whether this system is stable or not. So by using Routh-Hurwitz criteria or Routh stability criteria, we can find whether that system is stable or not, but we cannot find where are the poles. All we can tell how many poles are unstable poles, and whether, based on that we can tell whether that system is stable or not. Okay, so since it has 6 poles, we're going to start with the s to the power of 6. So first write down coefficients of all even order. So coefficient of s to the power of 6 comes over here, coefficient of s to the power of 4, coefficient of s square, coefficient of constant. Okay, the next row is s to the power of 5. Write down all the odd coefficients. So 2, not the odd coefficients, I mean to say odd order coefficient. So s to the power of 5 coefficient is 2, s cube coefficient is 12, and s coefficient is 16. Okay, that's how I wrote down those constants. Now the next one is s to the power of 4. Okay, so to get s to the power of 4, the constant here, s to the power of 4, how did I get this 2? So multiply these two, 8 times 2 minus 12 times 1 divided by this constant right there. Okay, so 8 times 2, 16 minus 12, which is 4 divided by 2, equal to 2. That's how I end up getting 2 there. The next one is 12. How did I get the 12 there? I'm going to keep these two elements are same, but I'm going to take the remaining these two elements. So to get 12, it's going to be 2 times 20 minus 16 times 1 divided by 2. So 40 minus 16, 24 divided by 2, which is 12. I end up getting 12 there. Now to get 16, I'm going to use the same two elements. The first column elements are going to be the same, okay, and the next column elements are going to change for each and every element there. So 16 and 0. So to get this 16, 2 times 16 minus 0 times 1, which is 0 over 2, I will end up with 16 there. Okay, that's how I found the elements in that row. Okay, now to find out the next element or next row, so this is going to be s cube. Okay, so we'll skip the first row, whatever the next two rows. Based on the next two rows, we're going to find the elements. So here I have 2, 2, 12, 2. So to get this, which is 12 times 2, these two, minus 12 times 2 divided by 2. Okay, so this element is 0. Okay, this element is 0. Now 2, 2, 16, 16, for sure this element is going to be 0. 2, 2, 0, 0, this element is going to be 0. So all the elements in one row are 0. Then we cannot proceed from here, because if you proceed, we'll end up getting zeros or undefined values. So to proceed from here, there is a different way. Okay, that way is take the above row, which is s to the power of 4. So write down that row, which is going to be 2 times s to the power of 4 plus 12 times this is s square plus 16 equal to take that as 0. It doesn't matter anyway. Now I'm going to differentiate this with respect to s. So when I differentiate this with respect to s, okay, we'll end up with 8s cube plus 24s plus 0 equal to 0. Okay. Now the s cube elements, now I'm going to I'm going to write down these constant, 8 here, 24 there, and 0 there. Okay, so that's how we're going to do. So if we have every element in that row is 0, then take the above row, make sure that the power of s to the power of 4, and you have to skip s cubed, so it's going to be s square. You have to skip s and the constant. Okay, so here I end up with 8 and 24 and 0 there. Now from here onwards it's the same. So s square, take these two and these two, which is 8 times 12 minus 24 times 2 divided by 8. That value is, so this is 48 by 8, this value is 6. Okay, let me eliminate that. So this value is 6. Now the next element, I'm going to keep the same first column and then the next one. So skip the second column here. So 8 times 16 minus 2 times 0 over 8. So we'll end up with 16 there. This is 16. Okay. Now s to the power of 1. S to the power of 1, if you don't have any element, we can take that as 0. So these two, which is 24 times 6 minus 16 times 8 over 6. That value is, this value is 16 over 6. Okay, if you want to simplify it, it's going to be 8 over 3. Okay, so the first term I end up with 8 over 3. Okay, the next one here, I'm going to use these two elements and these two elements, so I'll end up with 0 there. Okay, now s to the power of 0. So here I'm going to use these two elements, so 8 by 3 times 16 minus 6 times 0 over 8 by 3. These two get cancelled out, we'll end up with 16. Okay, so here we'll stop. Once we reach s to the power of 0, we'll stop it there. Now find out, are there any sign changes in this first column? If you don't have any sign changes, then this system is stable. Okay, so all the poles in the system, so if you look into the XY graph, so all the poles, as long as for any system, as long as poles are in this left hand side of the y-axis, then that system is stable. So here I don't have any sign changes, so that indicates that all the poles are on the left hand side. So this is a stable system. That's what we can find out by using this method. Now, two important points. If you have 0, I explained that in the previous video, but to clarify, if you have 0, if you have all zeros, what we did, we took the previous row and differentiated with respect to s. Okay, that's how we end up getting these elements, and then proceed with the same method what we did. Now if we have 0 in the first column, then we will take that as a very small positive number, and zeros at any other point, so 0 here, 0 here, 0, 0, all these zeros we will consider them as zeros. Only 0 in the first column we'll consider that as a very small positive number, because 0, it doesn't have positive or negative sign. So how do you know whether there is a there is an unstable pole here? So if we have 0, it's that means a pole might be at this point, at that point it's a marginally stable, but here we'll consider that as a very small positive number to make it as a assuming it as a stable pole. Okay, I'll stop this video here. I'll solve a couple of more examples in the next video. Thank you.